There is a way to stand on Earth and forget that the ground beneath you belongs to an ice age. The rivers move. Forests spread across temperate hills. Cities rise beside coastlines. And most winters end without any hint that kilometers of ice once covered large parts of the northern continents. From inside a single human lifetime, the planet can seem settled. But Earth is not settled. It is only passing through one climate state among many. For roughly the last 2.5 million years, large ice sheets have repeatedly expanded and retreated across the northern hemisphere. The colder intervals were long, the warmer intervals between them were shorter. We are living inside one of those warmer intervals now, the Holocene, which began about 11,700 years ago. That makes the present world feel less like the end of an ice age than a room inside one. The larger geological chapter is still here. Greenland remains capped by ice. Antarctica remains frozen. Mountain glaciers survive on several continents. Even in places where the ice has vanished, its old presence remains visible in carved valleys, lake basins, transported rock, and coastlines altered by changing seas. What changed after the last glacial period was not the existence of ice itself, but its reach. Great continental sheets withdrew, sea level rose, landscapes opened. Human societies eventually built farms, towns, roads, ports, and entire histories across terrain that earlier ice had shaped. So the question carried by this episode sounds simple. When does the ice return? It is tempting to imagine that there must be a schedule. The climate record contains recurring patterns, and Earth's orbit changes in calculable ways. The shape of the orbit shifts, the tilt of the axis changes, the direction of that axis slowly turns. Together, these motions alter how sunlight is distributed by latitude and season across spans of tens of thousands of years. They help pace the glacial cycles. But pacing is not the same as commanding. An ice sheet does not begin because a date arrives. Snow must survive summer after summer in the right northern regions. Ocean circulation must carry heat in particular ways. Atmospheric carbon dioxide changes the background temperature of the climate system. Snow and ice reflect sunlight, which can reinforce cooling once expansion begins. Land, ocean, atmosphere, and orbit all participate. This is why the familiar idea that Earth is simply overdue for another ice age can be misleading. The Holocene has lasted long enough to invite comparison with earlier warm periods. But those earlier intervals were not identical copies of one another. Orbital conditions differed. Carbon dioxide differed. Ice sheets began from different states. Even the rhythm that became prominent during the later Quaternary was never a metronome, ticking toward a fixed appointment, and the present has another difference. Human activity has changed the concentration of greenhouse gases in the atmosphere, adding a new influence to a climate system whose glacial rhythm was once governed without us. Modern modeling, therefore, places the next major glacial inception far beyond any near human horizon. Though the exact timing depends on assumptions about future carbon dioxide, orbital forcing, ice sheets, ocean circulation, and the long carbon cycle. Recent coupled modeling finds outcomes ranging across tens to well over 100,000 years, rather than imminent return of continental ice. The return of continental ice is not approaching like weather on tomorrow's horizon. It belongs to deep time. To understand what that means, we have to leave the present climate behind and follow ice much farther into Earth's past. Through worlds colder than anything civilization has known, until the repeating pattern itself begins to come into view. The first truly deep encounter with planetary ice lies so far behind the present that the continents themselves were arranged beyond recognition. More than 600 million years ago, during the Cryogenian period, Earth passed through at least two major episodes of glaciation. The older is called the Sturcian glaciation. The younger is the Marinoan. Together, they gave rise to one of the most arresting ideas in Earth science: Snowball Earth. The name sounds simple, but the science behind it is careful. Researchers do not imagine a planet frozen into one perfectly uniform sphere of solid ice from the surface of the oceans to the sea floor. The central idea is that ice may have reached very low latitudes, perhaps close to the equator, while much of the ocean surface became covered by ice. Exactly how complete that cover was remains a subject of study, with models ranging from a hard snowball to states that preserved patches or belts of open water. The evidence begins in stone. On several continents, geologists have found ancient sediments that carry the marks of glaciers. There are rocks dropped from floating ice. There are layers scraped and transported by moving ice. There are deposits that formed where glaciers once reached the sea. When researchers reconstruct the positions of those rocks at the time they formed, some appear to have been laid down at latitudes far closer to the equator than any large modern ice sheet reaches. That creates a physical puzzle. Ice near the equator is difficult to sustain because the tropics receive abundant sunlight. If glaciers truly reach those regions, the climate system must have crossed into a state very different from the one familiar today. One of the most important mechanisms is the reflectivity of ice. Open ocean is dark enough to absorb a large share of incoming sunlight. Snow and ice reflect much more of it back towards space. So as ice spreads, the planet absorbs less solar energy. That encourages further cooling, which allows still more ice to survive. The process is called ice albedo feedback. It does not create a glaciation by itself. Something has to push the climate toward colder conditions first. During the cryogenian, scientists have explored several contributing factors, including the arrangement of continents, long-term changes in volcanic carbon dioxide, and chemical weathering of exposed rock. Continents positioned in warm, wet tropical regions can weather rapidly, and that weathering removes carbon dioxide from the atmosphere over geological time. If enough greenhouse warming is lost, ice can advance. Once the bright surface grows large enough, the feedback can become powerful. A planet that begins cooling for one reason may continue cooling because its own expanding ice changes the amount of sunlight it keeps. There is an unusual calm in the scale of this process. Nothing needs to happen in a single winter. No one season has to be dramatic. Small imbalances can persist across spans longer than civilizations, longer than species, and eventually reshape the appearance of an entire planet. For life already present in the oceans, such a world would have been difficult, but not necessarily empty. Microbial ecosystems had existed for billions of years before the cryogenian. Photosynthetic organisms depended on light. Other organisms depended on chemical energy or on material produced by those photosynthesizers. A heavily ice-covered ocean would have changed access to sunlight, nutrients, and gases, yet life endured. Scientists have proposed several possible refuges. Some organisms may have survived beneath thinner or seasonally broken ice. Some may have occupied open water regions maintained by winds, currents, or local geography. Others may have lived around hydrothermal systems on the seafloor, where energy comes from chemistry rather than sunlight. The exact geography of survival remains uncertain, but the continuation of life beyond these glaciations is written into everything that came later, and the ice itself contained the beginning of its own ending. Even on a deeply frozen planet, volcanoes continue to release carbon dioxide. Under warmer conditions, part of that carbon is gradually removed through reactions involving rainwater, rock, rivers, and the ocean. But when broad areas of land are locked beneath ice and the hydrological cycle is greatly weakened, this long-term weathering thermostat changes. Volcanic carbon dioxide can then accumulate. Not quickly, the buildup may take millions of years. But geological time gives small yearly additions enormous patience. Eventually, greenhouse warming becomes strong enough to overcome the reflective surface. Melting begins in the regions most vulnerable to change. Darker ocean or land appears beneath retreating ice and absorbs more sunlight. The same kind of feedback that once helped the planet cool now assists the thaw. Geologists find another clue directly above many cryogenian glacial deposits, unusual carbonate layers often called cap carbonates. They appear abruptly after the Ice Age sediments and record a world undergoing rapid chemical and environmental change. Their exact formation involves processes still being refined, but they fit the broader picture of a sharp transition from severe glaciation into intense greenhouse conditions. The thaw would not have returned Earth immediately to anything resembling the modern climate. Oceans changed chemistry. Weathering accelerated. Sediments carried material from newly exposed continents into the sea. Carbon moved rapidly among atmosphere, water and rock, compared with the long frozen interval that came before. This is one reason Snowball Earth matters far beyond the image of a white planet. It shows that climate feedbacks can carry Earth into states that seem stable while they last, yet are not permanent. Ice can reinforce ice. Greenhouse gases can accumulate behind that frozen state. Weathering can pull carbon back down again. The planet is not governed by one switch, but by interacting processes working on different clocks. The cryogenian glaciations also leave a useful warning against simple repetition. Later, ice ages were not smaller copies of Snowball Earth. The continents were different. The atmosphere was different. The sun was slightly fainter. Life was different. Ocean circulation was different. The physics of reflected sunlight still mattered, but the surrounding world had changed. After the Marinoan ice retreated, Earth continued into the final part of the Precambrian. The planet would never simply repeat the same frozen state on a fixed schedule. Yet the deep lesson remained in the climate system. Under the right conditions, ice can become more than a consequence of cooling. It can become part of the machinery that keeps the cooling going. And once that idea is carried forward through time, the later ice ages begin to look less like isolated disasters and more like different expressions of a planet continually balancing sunlight, atmosphere, ocean, rock, and the slow movement of continents. Hundreds of millions of years after the cryogenian ice disappeared, Earth found another path into a long cold interval. This time, the planet did not become a nearly white sphere. Instead, ice gathered across the southern continents while tropical forests flourished thousands of kilometers away. The contrast was immense, glaciers advancing over one part of the world, warm wetlands growing beneath equatorial sunlight on another. Geologists call this broad interval the Late Paleozoic Ice Age. It began in the closing part of the Devonian and became especially prominent through the Carboniferous and early Permian. Roughly 360 to 260 million years ago, it was not one uninterrupted freeze. Ice sheets expanded, shrank, disappeared from some regions, and returned to others in a succession of glacial phases lasting tens of millions of years. The geography of the planet helped make this possible. Much of the land that would eventually become South America, Africa, Antarctica, Australia, and India was joined within Gondwana. Large portions of this southern landmass lay close enough to the pole for snow to persist across summers. Once ice sheets formed, their reflective surfaces helped maintain colder conditions, much as ice albedo feedback had done in much older climates. But the late Paleozoic world contained another powerful influence. Its atmosphere was being reshaped by life. Across the humid tropics, broad lowlands supported dense forests dominated by plants, unlike those surrounding modern cities and farms. Giant lycopsids rose above wetlands. Horsetails grew to tree-like proportions. Early seed plants spread through drier regions. Ferns and other vegetation filled landscapes threaded with shallow water. These forests pulled carbon dioxide from the atmosphere through photosynthesis. Some of that carbon returned quickly when organisms respired or plant material decayed, but wet, oxygen-poor environments could preserve large amounts of dead vegetation long enough for it to become buried beneath sediment. Layer after layer accumulated in sinking basins. Over geological time, pressure, heat, and burial transformed portions of that organic material into the coal deposits found today across North America, Europe, Asia, and other regions that once lay within carboniferous wetlands. The process removed carbon from the active atmosphere and ocean system for very long periods. It would be too simple to say that forests created the Ice Age. Climate does not usually offer such a single cause. Tectonics determined where continents stood. Mountain building altered weathering. Ocean gateways influenced circulation. Volcanic activity supplied carbon dioxide. The evolving biosphere changed how carbon moved between air, water, soil, sediment, and rock. But carbon burial was part of the larger balance. When carbon dioxide falls, the atmosphere becomes less effective at retaining outgoing heat. If geography and seasonal sunlight are already favorable for ice, lower greenhouse gas concentrations can make glaciation easier to sustain. The result was a planet divided by latitude. Near the equator, humid forests could remain productive beneath warm skies. Farther south, immense ice sheets occupied parts of Gondwana. Between them lay broad climatic zones that shifted as the glaciers advanced and retreated. There is something useful in this coexistence. An ice age does not require every place on Earth to be cold. Even during severe glacial intervals, the tropics may remain warm, forests may survive, oceans remain open. Rain continues to fall. What defines an icehouse climate is the long-term presence and repeated growth of large ice sheets, not a planet-wide winter. The late Paleozoic record preserves those movements in stone. Sediments carried by glaciers appear across lands, now separated by oceans. Scratches left beneath moving ice are preserved in old rock surfaces. Deposits once laid down near glacial margins can be followed through layers that record repeated environmental changes. Elsewhere, sediments accumulated in shallow tropical seas while sea level rose and fell. When continental ice expanded, enormous quantities of water became stored on land. Global sea level dropped. When the ice retreated, water returned to the ocean and coastlines moved inland again. Across the Carboniferous world, these changes occurred repeatedly. In some regions, the resulting sedimentary layers form sequences in which marine deposits alternate with river, delta, soil, and coal-bearing beds. A single location could move from coastal water to exposed land and back again, without traveling anywhere at all. The shoreline moved instead. Those repeating layers contain an early version of a pattern that will become increasingly important later in our journey. Earth's ice responds to more than one clock. The atmosphere can change over millions of years. Continents drift on still longer timescales. Yet within an icehouse world, smaller variations in sunlight caused by the planet's orbital motions can help pace the advance and retreat of glaciers. Evidence from late Paleozoic sediments suggests that astronomical cycles influenced some of these repeated climate changes even hundreds of millions of years ago. The exact continents were different. The atmosphere was different. The organisms were different. But the planet was already moving through the same basic celestial motion. Its orbit changed shape slightly. Its axis tilted by varying amounts. The direction of that axis slowly shifted. Those motions altered the seasonal distribution of sunlight, creating subtle changes that could be amplified when the climate system was sensitive enough. An orbital change alone did not have to build an ice sheet. It only had to alter summer conditions where ice was already capable of surviving. This distinction matters. A small change in sunlight can become important when snow, carbon dioxide, ocean circulation, and continental geography are already positioned near a threshold. The same orbital variation may have a far weaker effect in a greenhouse world, with no large ice sheets and much higher concentrations of carbon dioxide. The planet responds according to the state it is already in. Even the unusual animals of the Carboniferous belonged to that state. Atmospheric oxygen reached levels higher than those of the modern world, although estimates vary through the period. Some arthropods became much larger than their modern relatives. The famous Meganeura, an insect related to dragonflies and damselflies, carried wings spanning well over 1/2 meter. Its existence is often associated with elevated oxygen, though oxygen alone does not explain every detail of arthropod size. Ecology, development, temperature, and the absence or presence of particular predators may also have mattered. The broader point is quieter. The air itself was different. A person, somehow placed in one of those forests, would not have encountered a primitive version of the modern world. The plants would be unfamiliar. The animals would be unfamiliar. Continents would sit in unfamiliar places. Even the composition of the atmosphere would carry the signature of biological and geological processes, operating in combinations that no longer exist. Yet one familiar substance would surround much of the southern landscape: ice. For millions of years, it grew and retreated across Gondwana, responding to changes in carbon, sunlight, and geography. Eventually, the conditions supporting widespread glaciation weakened. The configuration of continents continued to evolve. Atmospheric carbon dioxide rose from its lower Paleozoic levels. Patterns of weathering and organic carbon burial changed. Volcanism and tectonic activity continued feeding the long carbon cycle. By the later Permian, the great southern ice sheets had largely disappeared. Earth moved toward a warmer climate that would dominate much of the Mesozoic era. The glaciers did not return simply because enough time passed. They returned only when the planet again assembled the necessary conditions. That is one of the clearest messages carried forward from the late Paleozoic. Ice ages have history, but they do not have appointments. Their timing emerges from a meeting of processes: continents moving across latitudes, rocks reacting with air and water, organisms storing carbon, volcanoes returning it, oceans transporting heat, and the planet's orbit continually altering the sunlight of the seasons. Far in the future of that Carboniferous forest, another configuration would begin to form. The southern continents would separate. Ocean passages would open. Mountains would rise. Atmospheric carbon dioxide would decline from the high levels of later greenhouse worlds. And after a long interval with little permanent ice, the planet would begin cooling again. This time, the ice would eventually arrive in a world whose continents were beginning to resemble our own. For a long time after the great southern glaciers of the Paleozoic disappeared, Earth returned to a warmer way of being. During much of the Mesozoic era, permanent continental ice was limited or absent. Sea level was often high. Warm oceans reached far toward the poles. Even after the age of dinosaurs ended, the early Cenozoic continued this greenhouse inheritance. By the early Eocene, more than 50 million years ago, Earth was much warmer than it is today. Forests extended into high latitudes. Fossils from the Arctic preserve evidence of environments that would seem misplaced there now, including broadleaf vegetation and animals adapted to climates far milder than the modern polar world. Antarctica was not yet buried beneath a continent-scale ice sheet. The planet still had seasons. Snow still fell in some places, but the stable polar ice caps that now define Earth had not yet taken their modern form. Then the long cooling began, not as a single collapse, not as one dramatic threshold crossed in one century. It unfolded across millions of years. Atmospheric carbon dioxide gradually declined from the high levels of earlier greenhouse climates. Tectonic changes altered the shape of continents and the pathways available to ocean currents. Mountain building exposed fresh rock to weathering, allowing chemical reactions to remove carbon dioxide from the atmosphere over long spans of time. Biological processes continued moving carbon between air, ocean, sediment, and living systems. The entire background state of the planet was changing. One place became especially important: Antarctica. Today it is easy to imagine Antarctica as a natural home for ice, as though a continent sitting over the South Pole must inevitably be frozen. But latitude alone is not enough. For tens of millions of years, Antarctica occupied high southern latitudes without carrying anything like its present ice sheet. A continent can sit near a pole and remain comparatively warm if the atmosphere contains enough greenhouse gases and if ocean circulation transports sufficient heat toward it. The appearance of permanent Antarctic ice required more than geography. Around 34 million years ago, near the boundary between the Eocene and Oligocene epochs, the climate crossed into a colder state. Evidence from marine sediments shows a major change at this time. Oxygen isotopes preserved in microscopic shells record a combination of falling ocean temperatures and growing continental ice. Ice began accumulating on Antarctica at a scale large enough to alter global sea level. The planet had entered a new icehouse phase. Carbon dioxide appears to have played a central role. As atmospheric concentrations declined, the greenhouse effect weakened. Under the right orbital conditions, Antarctic summers became cool enough for snow to persist more effectively from one year into the next. Once ice remained through summer, familiar feedbacks could begin working. A brighter surface reflected more sunlight. Higher ice surfaces reached colder air. Growing glaciers changed local circulation and elevation. And as the ice sheet expanded, Antarctica became increasingly capable of maintaining a climate very different from the one it had known before. Ocean circulation was changing as well. The continents surrounding Antarctica were slowly separating from it. Passages developed between Antarctica and South America and between Antarctica and Australia. Over time, these changes helped create a continuous oceanic route around the southern continent. That route eventually allowed the Antarctic Circumpolar Current to flow around Antarctica. This current is now the most powerful system of ocean circulation on Earth by volume. It connects the Atlantic, Pacific, and Indian Oceans while helping isolate Antarctica from some of the warmer waters farther north. For many years, the opening of southern ocean gateways was often treated as the decisive event that froze Antarctica. The modern picture is more nuanced. The timing of gateway opening, the development of the circumpolar current, atmospheric carbon dioxide decline, orbital variations, and ice sheet growth do not reduce neatly to a single cause and effect. They interacted over time, and researchers continue refining how much influence each process had during different stages of Antarctic cooling. The useful lesson is not that one current created an ice sheet. It is that planetary climate can change when several slow processes begin reinforcing one another. Antarctica was becoming more isolated. Greenhouse warming was weakening. Orbital conditions periodically favored colder summers. And once substantial ice developed, the ice itself became part of the climate system. From that point onward, Earth was no longer a planet without major permanent ice. But it still did not look like the glacial world familiar from the recent geological record. For millions of years, the northern hemisphere remained comparatively free of the enormous continental ice sheets that would later cover Canada, Scandinavia, and parts of northern Eurasia. The south had become deeply glaciated. The north had not yet followed. there is a strange asymmetry in that interval. Imagine looking at Earth from far above around 20 million years ago. At one end of the planet, Antarctica already carries a large mass of ice. At the other, the Arctic Ocean exists beneath a different climatic regime, surrounded by continents that have not yet been repeatedly buried beneath kilometer-thick glaciers. The familiar two-pole icehouse world is still incomplete. Then the planet continued cooling. Tectonic changes reshaped ocean connections. Mountains rose. Weathering continued altering atmospheric carbon dioxide. The Arctic became colder. Seasonal snow survived more easily across high northern landscapes. By roughly 3 million years ago, the climate was approaching another threshold, and around 2.7 million years ago, large northern hemisphere ice sheets began expanding much more extensively and repeatedly. The reasons remain an active field of study, because no single event explains the transition. Atmospheric carbon dioxide was already relatively low compared with earlier Cenozoic greenhouse climates. Changes in ocean circulation may have altered how heat and moisture moved through the North Atlantic and Arctic. The uplift of major mountain ranges changed atmospheric circulation and weathering. The closing and restriction of ocean gateways modified the exchange of water between basins, and orbital variations continued, changing the amount of summer sunlight reaching high northern latitudes. Once again, the important condition was not simply cold winters. It was cool summers. Snow falling during winter does not create a continental ice sheet if summer removes it completely. Glaciation becomes possible when enough snow survives the warm season. The remaining snow increases surface brightness, helping the region absorb less sunlight. Additional snow accumulates the next year. Layers compress. Air is squeezed from them. Snow becomes firn, then glacial ice. Given enough time, the ice thickens until its own weight causes it to flow outward. A glacier begins to reshape the land beneath it. When this happens over areas the size of countries, the climate system changes with it. The northern ice sheets that emerged near the end of the Pliocene would eventually become some of the largest moving features on the planet. Over later glacial cycles, ice spread across much of Canada. It reached into the northern United States. Scandinavian ice expanded across northern Europe. Other ice masses occupied regions of Eurasia and mountain systems farther south. Their weight depressed the crust. Their movement carved valleys. Their meltwater reorganized rivers. Their storage of ocean water lowered sea level enough to expose broad areas of continental shelf. Places now separated by ocean became connected by land. The geography available to animals, plants, and eventually human beings shifted with the ice. Around 2.58 million years ago, geologists placed the beginning of the Quaternary period. This is the geological interval we still inhabit. It is marked by repeated glacial and interglacial cycles, along with the evolution and spread of the genus Homo, and, much later, our own species. For much of the Quaternary, the glacial rhythm differed from the pattern most people hear about today. Early cycles were strongly associated with a roughly 41,000-year variation related to the changing tilt of Earth's axis. Then, somewhere between about 1.2 million and 700,000 years ago, the character of the cycles changed. Large ice sheets began persisting longer. The dominant glacial rhythm shifted towards cycles, averaging close to 100,000 years. Scientists call this the mid-Pleistocene transition. Its existence is clear in marine climate records. Its full explanation is not. There was no corresponding new 100,000-year orbital forcing suddenly appearing at the same strength as the climate response. Instead, something within the Earth system changed the way ice sheets responded to the orbital variations already present. Researchers have proposed several contributing processes. Long-term changes in carbon dioxide may have mattered. Repeated glaciations may have gradually removed loose sediment beneath northern ice sheets, allowing later glaciers to anchor but more strongly onto bedrock and grow thicker. Ice sheet dynamics may have developed thresholds that favored longer build-up followed by rapid retreat. Ocean circulation and interaction among different orbital cycles may also have contributed. The result was the rhythm preserved so clearly in late Pleistocene climate records. Long glacial intervals, shorter warm intervals, ice advancing then withdrawing, sea level falling then rising, carbon dioxide moving with the climate, dust crossing continents, vegetation zones migrating north and south, ocean currents reorganizing. The world repeatedly remade without ever returning to precisely the same starting point. This is much closer to the Earth that eventually inherited us. The ice sheets of the recent past were not remnants of Snowball Earth. They were not echoes of Carboniferous glaciers returning on an enormous calendar. They belonged to a new climate system. A world with continents in nearly modern positions. A large Antarctic ice sheet already established. An Arctic capable of seasonal sea ice. Northern land masses positioned where continental glaciers could grow. Greenhouse gas concentrations low enough for orbital changes to matter strongly. And an evolving collection of feedbacks capable of turning modest changes in seasonal sunlight into enormous changes across the surface of the planet. By the time early humans appeared, the rhythm was already underway. No one started it. No civilization had to witness its beginning. Generation after generation simply entered a world in which coastlines, rainfall, vegetation, and migration routes were being shaped by a climate pulse older than humanity itself. And above all of it, almost unnoticed, Earth continued moving around the sun in a path that was never quite the same from one age to the next. The ice had found its rhythm. The next step is to understand the celestial motions that helped keep time. The rhythm of the ice ages begins far from any glacier. It begins with geometry. Earth does not travel around the sun in exactly the same way forever. Its orbit changes shape. Its axis changes tilt. The direction that axis points slowly turns through space. None of these motions is large enough to feel beneath your feet, and none changes quickly enough to notice across a lifetime, but given tens of thousands of years, they rearrange sunlight across the planet. They do not change the sun itself. They change where sunlight falls, when it falls, and how strongly particular seasons receive it. The first motion is eccentricity. Earth's orbit is not a perfect circle. It is a slightly stretched ellipse, and the amount of that stretching changes over long periods as the gravity of other planets, especially Jupiter and Saturn, subtly alters Earth's path. At some times, the orbit is closer to circular. At others, the difference between Earth's nearest and farthest distances from the Sun becomes somewhat greater. One of the important eccentricity cycles occurs on a timescale of roughly 100,000 years, with longer variations layered beneath it. By itself, eccentricity does not create a large change in the total annual sunlight Earth receives. Its importance comes partly from the way it modifies another cycle. That second motion is precession. Earth spins like a top, but the axis of a spinning top does not remain pointed in one fixed direction. It traces a slow circle. Earth does something similar. Today, the northern end of the axis points close to Polaris. Thousands of years from now, it will point elsewhere. Across a cycle of roughly 26,000 years, the orientation changes as the axis slowly turns. At the same time, the orientation of Earth's elliptical orbit also shifts. Together, these motions alter the relationship between the seasons and Earth's changing distance from the Sun. Today, Earth reaches its closest point to the Sun during Northern Hemisphere winter. That does not make the Northern Hemisphere warmer than the Southern Hemisphere overall, because seasons are controlled mainly by axial tilt, not distance from the Sun. but over thousands of years. Precession changes which season occurs near the closest and farthest parts of the orbit. There are times when Northern Hemisphere summer occurs nearer perihelion, making those summers somewhat more intense. At other times, northern summer occurs farther from the sun and receives less seasonal reinforcement. Eccentricity determines how much this distance difference matters. When the orbit is nearly circular, precession has a smaller effect on the contrast. When the orbit is more elliptical, the seasonal consequences can be stronger. Then there is the third motion, obliquity. Earth's axis is tilted relative to the plane of its orbit. That tilt is the reason the planet has seasons. But the angle is not fixed. Over a cycle of roughly 41,000 years, Earth's axial tilt changes between about 22 and a little more than 24 degrees. The difference sounds small. For ice sheets it matters. Greater tilt gives higher latitudes stronger summer sunlight and darker winters. Lower tilt reduces summer sunlight at high latitudes. And for the growth of continental ice, summer can matter more than winter. This is one of the most important ideas in the story of glaciation. An extremely cold winter can produce enormous snowfall, but if the following summer melts all of it, then ice sheet cannot grow. For glaciers to expand across continents, some winter snow must survive the warm season. Then, another winter adds new snow and another. As the surviving layers accumulate, their weight compresses the snow below. Over time, the structure changes. Loose flakes become firn. Firn becomes dense glacial ice. The landscape begins storing winter, year after year, century after century. A weak summer can therefore matter more than a severe winter. This is why paleoclimate researchers pay particular attention to summer sunlight at high northern latitudes. The northern hemisphere contains broad land areas. At the latitudes where continental ice sheets can form, North America and Eurasia provide enormous surfaces upon which snow can accumulate. Around the South Pole, Antarctica already occupies the main landmass, while much of the comparable latitude band elsewhere is oceans. Ocean and land respond differently to seasonal heating. Land can support thick continental ice. Open ocean cannot build a land-based ice sheet, so the geometry of northern summer sunlight becomes a sensitive part of the glacial system. The three orbital motions are often grouped under the name Milankovitch cycles, after the Serbian mathematician and geophysicist Milutin Milankovitch, who spent decades calculating how orbital changes could influence Earth's climate. The idea was not that a single cycle would mechanically switch an ice age on and off. The climate record is more complicated than that. Instead, orbital variations provide changing patterns of seasonal energy. The Earth system responds. Snow responds. Ice responds. Vegetation responds. Oceans respond. Carbon dioxide and methane respond. Dust responds. Sea level responds. The initial astronomical signal may be modest, but feedbacks can enlarge its climatic consequences. This became much clearer during the 20th century, when scientists learned to read climate history from marine sediments. Tiny organisms living in the ocean build shells that eventually fall to the seafloor. Layer upon layer accumulates over long intervals. The chemistry of those shells preserves information about the temperature of seawater and the amount of ice stored on land. When researchers analyzed long sediment cores, they found appeared near the same frequencies. Some appeared near the frequencies predicted, roughly 23,000 years, roughly 41,000 years, roughly 100,000 years. The match provided strong evidence that celestial geometry was helping pace the climate cycles recorded in the oceans. But it also deepened the puzzle. The 100,000-year glacial rhythm of the later Pleistocene is much stronger in the climate record than might be expected from the comparatively weak direct effect of eccentricity on incoming solar energy. This became known as the the 100,000-year problem. Why should a relatively subtle orbital variation correspond so clearly with enormous changes in ice volume? Part of the answer appears to lie in the non-linear behavior of ice sheets and climate feedbacks. Large ice sheets do not grow and shrink in a perfectly proportional response to sunlight. They have thresholds. They reshape the land beneath them. They alter atmospheric circulation. They modify regional temperature. They interact with oceans. Their elevation changes as they grow. Their edges can remain stable for long periods and then retreat much faster when conditions cross a critical range. The climate system also contains carbon feedbacks. During glacial periods, atmospheric carbon dioxide tends to be lower. During interglacials, it tends to be higher. These changes are not simply a direct consequence of one cause. They involve the ocean, biological activity, circulation, temperature, sea ice, and the exchange of carbon among different reservoirs. But once carbon dioxide changes, it alters the planet's energy balance. Orbital forcing can begin the movement. Feedbacks can carry it farther. This is why the orbital cycles are better understood as pacing mechanisms than as a clock with fixed appointments. They influence the timing of glacial change, but the response depends on the state of the entire climate system. A particular combination of orbit and tilt might favor glaciation when atmospheric carbon dioxide is low, and large northern ice sheets are already present. The same configuration might produce a much smaller effect in a warmer greenhouse world. The celestial rhythm continues. The planet decides how strongly to answer. Long before anyone could calculate these cycles, human beings were already sensitive to the simpler patterns in the sky. Communities watched the changing position of sunrise and along the horizon. They followed the seasons of particular stars. They used repeated celestial motions to decide when to travel, plant, harvest, gather, or return. The great orbital variations were far too slow to recognize within a human lifetime. Yet they belong to the same underlying fact. Earth's relationship with the sky is never static. A shadow changes through a day. A sunrise moves through a year. The stars shift through centuries. And across far longer spans, the planet's orientation and orbit reshape the seasons themselves. No observer, standing beneath a night sky, could watch an obliquity cycle unfold. A single person would see almost none of it. Even a civilization lasting several thousand years would witness only a small fraction. But ice remembers what people cannot. So do ocean sediments, so do cave deposits. So does pollen buried in old lake beds, so does dust trapped in Antarctic ice. Taken together, these records allow a patterns slower than civilization to become visible, and they reveal another feature of glacial time. The descent into an ice age and the escape from one are not mirror images. Large ice sheets often build over many tens of thousands of years. Then, near the end of a glacial period, major warming and ice loss can occur much more rapidly on geological timescales. These transitions are called deglaciations or terminations. The most recent one began as the last glacial world moved toward the warmer conditions that eventually became the Holocene. Ice retreated, sea level rose, carbon dioxide increased, vegetation zones migrated, ocean circulation changed. But even this transition was not smooth. There were reversals and pauses. The climate moved in steps. The last glacial period, therefore, did not end because one orbital cycle reached a simple maximum. It ended through interactions and between changing sunlight feedbacks operating through ice, ocean, atmosphere, and carbon. This complexity is the reason the phrase "every 100,000 years" can be useful as a broad description and misleading as a prediction. Cycles do not repeat with the precision of an alarm. Their spacing varies, their duration varies, their intensity varies. Interglacials differ from one another. The shape of each transition depends on conditions inherited from what came before, and in this matters when we look at the warm interval surrounding us now. If the ice ages were controlled by a perfectly repeating timer, predicting the next one would require little more than counting years since the last glacial retreat. But Earth does not work that way. To ask when the ice returns, we have to know more than how long the Holocene has lasted. We have to know what the orbit is doing now. We have to know how the present orbital configuration compares with earlier interglacials. And we have to account for something that no previous quaternary interglacial contained in the same form. A species capable of altering the atmospheric concentration of greenhouse gases on a planetary scale. The orbital cycles are still moving. The axial tilt is still changing. Precession continues. Eccentricity continues. The astronomical machinery has not stopped. But the climate system receiving those signals is no longer identical to the one that received them before human civilization began. And that is where the old rhythm of ice meets the modern atmosphere. The most recent great ice sheets were still near their maximum extent only about 20,000 years ago. Across North America, the Laurentide ice sheet covered most of Canada and reached into what is now the northern United States. Another large ice mass occupied parts of western Canada. Across northern Europe, the Scandinavian ice sheet extended over much of the region. Mountain glaciers were larger on nearly every continent. So much water was stored on land that global sea level stood more than 100 meters below the modern shoreline. The map of the world was different. The Bering Strait was exposed as dry land, joining Siberia and Alaska across a broad region now called Beringia. The North Sea contained areas that could be crossed on foot. Australia and New Guinea were joined within a larger landmass. Islands were connected that today are separated by shallow seas. These were not minor coastal adjustments. Entire migration routes existed where ocean now stands. Then the balance began to change. Northern summer sunlight increased in ways that favored melting. Ice sheets started losing more mass during warm seasons. As their surfaces lowered, they entered warmer air. Darker ground appeared around retreating margins and absorbed more sunlight than snow and ice had reflected. Carbon dioxide rose from its glacial concentration. Methane increased as well. Ocean circulation reorganized. The climate moved toward a warmer state, but not in one clean motion. The retreat from the last glacial maximum took thousands of years and contained abrupt regional shifts. One of the most important involved the North Atlantic. As northern ice sheets melted, large amounts of fresh water entered the ocean. Fresh water is less dense than salty water, and major changes in its distribution can influence the sinking and circulation of North Atlantic waters. The climate system responded unevenly. Some regions warmed rapidly. Others returned to colder conditions for centuries. Near the end of the last glacial period, a cold interval, known as the Younger Dryas, interrupted much of the warming around the North Atlantic. It began roughly 12,900 years ago and ended about 11,700 years ago. Greenland ice cores record the transition with remarkable sharpness. Temperatures over Greenland rose rapidly as the Younger Dryas ended, though the exact magnitude and speed differed from place to place. What matters for the larger story is that deglaciation was capable of producing abrupt regional changes even while the planet was moving toward a warmer long-term state. The climate did not glide smoothly out of the glacial world. It crossed thresholds. It adjusted through the atmosphere and ocean. It carried the memory of melting ice. Then came the Holocene. Around 11,700 years ago, the period recognized as the current geological epoch began. The immense northern ice sheets continued shrinking after that boundary. Sea level continued rising. Forests moved into newly available regions. Lakes formed behind retreating glaciers. Rivers established new channels across terrain that had been scraped, compressed, and buried beneath ice. Human beings were already present across large portions of the planet. For most of our species' existence, people had lived through the variable climates of the Pleistocene. Homo sapiens had evolved long before the Holocene. Our ancestors had known colder worlds, warmer intervals, prolonged droughts, shifting coastlines, changing ecosystems, and landscapes altered by glacial advance and retreat. The beginning of the Holocene did not create humanity, but it did provide the climatic background in which agriculture expanded independently in several regions and increasingly large permanent settlements became possible. Over the following millennia, cultivated landscapes spread, villages became towns. Some towns became cities. Writing appeared in several societies. States and empires rose and disappeared. Trade routes crossed continents and oceans. Nearly everything, commonly called recorded history, unfolded within this one interglacial interval. That fact can make the Holocene seem suspiciously fragile. If recent warm periods lasted only a limited number of millennia, perhaps our own must be nearing an expiration date. The reasoning feels intuitive. It is also where the comparison begins to fail. Interglacials do not have a standard lifespan. Some previous warm intervals were relatively brief. Others persisted much longer. Their duration depended in part on the orbital configuration that controlled high-latitude summer sunlight, as well as on greenhouse gases and the size of surviving ice sheets. One useful comparison lies more than 400,000 years in the past. This interval is commonly associated with marine isotope stage 11. It attracted scientific interest because parts of its orbital configuration provide a better comparison with the Holocene than simply taking the immediately preceding interglacial. Earth orbital eccentricity during both intervals was relatively low. That matters because low eccentricity weakens the seasonal influence of precession. Under such conditions, the decline of northern summer sunlight can be prolonged rather than producing the simple pattern expected from a more strongly elliptical orbit. Marine isotope stage 11 was a long interglacial. Depending on how its boundaries are defined, relatively warm conditions persisted for well over 10,000 years, and some measures indicate a much longer interval without full-scale northern glaciation. The comparison is not perfect. No past interglacial is an exact duplicate of the present. The geometry of the orbit never repeats in precisely the same combination. Ice sheets begin from different sizes. Carbon dioxide concentrations differ. Ocean circulation inherits different conditions. Vegetation and dust patterns vary. But stage 11 demonstrates something important. An interglacial lasting beyond the age of the Holocene is not an anomaly. There is no geological rule requiring major glaciation, simply because roughly 12,000 years of warmth have passed. Another familiar comparison is the last interglacial, which occurred roughly 125,000 years ago. It is often called the Eemian in European records. During parts of that interval, high northern latitudes received stronger summer sunlight than they do today. Temperatures in some regions were warmer. Greenland contained less ice than at present, although it didn't disappear. Global sea level was several meters higher than today, with contributions from both Greenland and Antarctica. Then orbital conditions changed. Northern summer sunlight weakened. The climate slowly moved toward renewed glaciation. But even here, the transition cannot simply be copied and placed over the Holocene. The orbital path leading out of the last interglacial differed from the path Earth follows now. This is the central difficulty in asking whether our warm period is overdue to end. Time since the last glaciation is not the controlling variable. The climate does not count years. It responds to energy. It responds to carbon dioxide. It responds to the distribution of snow and ice, it responds to ocean circulation, vegetation, dust, and the geometry of the orbit. Two interglacials can reach the same age while facing very different futures. The present orbital configuration provides a good example. Earth's orbit is currently close to circular, compared with times of greater eccentricity. Axial tilt is gradually decreasing. Precession continues altering the seasonal relationship between Earth and the Sun. These changes influence northern summer sunlight, but their combination does not create the kind of rapid progression toward strong glacial conditions that a simple repeating calendar might suggest. Without human influence, researchers have long debated how far into the future the present interglacial might have continued before conditions became favorable for another glacial inception. Different modeling approaches have produced different answers. Some early comparisons suggested that glaciation could become possible within several tens of thousands of years. Other work emphasized the unusually weak orbital forcing of the present interval and proposed a naturally long interglacial, perhaps comparable in some respects with marine isotope stage 11. The disagreement was not evidence that orbital theory had failed. It reflected the sensitivity of glacial inception to small differences in assumptions. How low must northern summer sunlight become? How much carbon dioxide can remain in the atmosphere before snow fails to survive summer? How quickly does vegetation respond? How does ocean circulation redistribute heat? How large must persistent snowfields become before ice sheet feedbacks begin to strengthen? These questions involve thresholds rather than a single date. Imagine a northern landscape receiving snow through a series of winters. For a glacier to begin, the first important change may be almost unremarkable. A patch of snow remains through one summer. The next winter covers it. Some survives again. Over many years, the surviving area grows. The snow beneath becomes compact. A small perennial ice body forms. Eventually, if summers remain favorable, the process begins to reinforce itself. But if summers warm just enough, the accumulation disappears. The threshold is crossed in the other direction. This makes glacial inception sensitive to surprisingly small differences in the climate background. Carbon dioxide is one of those differences. Before industrialization, atmospheric carbon dioxide during the Holocene remained within the range characteristic of recent interglacials, though its history across the last several thousand years has prompted debate over the influence of early agriculture and land use. Whatever role pre-industrial societies may have played, the change beginning with large-scale fossil fuel combustion belongs to a different magnitude and rate. Coal, petroleum, and natural gas contain carbon stored away from their atmosphere for geological periods. When burned, part of that carbon becomes carbon dioxide. The atmospheric concentration rises. The ocean absorbs some of it. Plants and soils absorb some. The remainder accumulates in the air, strengthening the greenhouse effect. This modern increase has already moved atmospheric carbon dioxide far above the natural range preserved in Antarctic ice cores covering the last 800,000 years for the question of the next ice age that matters for a simple physical reason. Glacial inception requires sufficiently cool summers for snow and ice to survive at high northern latitudes. Additional greenhouse warming works against that requirement. This does not mean orbital cycles have stopped. They continue on their calculated paths, nor does it mean Earth has left the broader quaternary icehouse state overnight. Antarctica and Greenland still hold enormous ice sheets. The planet still carries the geography and polar conditions of an icehouse world. But the atmosphere through which the orbital signal now operates has changed. That change alters the threshold. A small shift in seasonal sunlight that might have favored expanding snow under a lower carbon dioxide concentration can produce a different result. when the background climate is warmer, the old orbital rhythm remains. The response of the climate system changes. There is a useful distinction here between delaying an ice age and preventing ice from ever returning. They are not the same claim. On sufficiently long timescales, carbon dioxide added today will not remain entirely in the atmosphere. The ocean and rocks continue participating in the carbon cycle. Chemical weathering gradually removes carbon dioxide. Carbon is transferred into sediments. Geological processes operate over spans, political, technological, or even civilizational planning. Eventually, the atmosphere will continue evolving, continents will continue moving. The sun itself will slowly brighten over geological time. Future glaciation must therefore be considered within a planet that will keep changing long after the present human era. No serious calculation can assign a permanent end to ice ages based only on present emissions. What can be studied is the nearer geological future, and on that scale, the effect is substantial. Modeling studies indicate that elevated carbon dioxide can postpone the next major northern hemisphere glaciation for tens of thousands of years and potentially much longer, depending on how much carbon is ultimately released and how slowly it is removed. The result is almost an inversion of the original question. At first, the puzzle seems to be whether the ice is late. Then the orbital record suggests that there was never a fixed appointment. And finally, the atmosphere reveals that the threshold itself has been moved. The world outside may still contain familiar winter snow. Mountain glaciers may still descend through cold valleys. Greenland may still shine white beneath polar daylight. But the processes that create a continental glaciation belong to a scale far larger than any one winter, decade, or century. They require the right combination of summers, the right orbital geometry, a sufficiently cool atmospheric background, and enough time for snow to begin remembering one year after another. For most of the recent geological past, those conditions assembled without any species understanding what was happening. This time, one part of the system has changed through human action. The next chapter of Earth's glacial rhythm, therefore, cannot be read from the old record alone. The rocks and ice cores tell us how the planet behaved before us. The atmosphere tells us why the future will not simply repeat it. The altered atmosphere changes the question in a subtle way. Instead of asking when the next glaciation should arrive, researchers have to ask what combination of orbital conditions and greenhouse gas concentrations would be required for one to begin at all. That is a harder problem. The astronomical part can be calculated far into the future with considerable precision. Earth's eccentricity, axial tilt, and precession follow gravitational patterns that can be projected across many thousands of years. The climate response is less mechanical. Ice sheets depend on thresholds. If high northern latitudes receive summers cool enough for enough snow to survive, perennial snowfields can expand. If the background atmosphere remains just a little warmer, the same orbital configuration may fail to produce lasting ice. This is why estimates for the next natural glacial inception have never reduced to one universally accepted date. Different models represent ice sheets, vegetation, carbon cycling, oceans, and atmospheric feedbacks in different ways. Some experiments begin with a climate untouched by industrial emissions and ask when orbital conditions alone might eventually favor renewed glaciation. Others include the carbon dioxide already added by human activity. Still others explore possible future emissions and the long time required for that carbon to be removed from the atmosphere-ocean system. The answers spread across a broad range, but one conclusion appears repeatedly. The next glaciation is not imminent. Even under natural conditions, the present orbital configuration does not strongly favor a rapid descent into a new continental ice age. And with elevated greenhouse gas concentrations, the threshold is pushed farther away. This gives the modern climate story an unusual relationship with deep time. Human societies tend to measure environmental change in years and decades. Orbital climate cycles unfold across tens of thousands of years. Yet carbon released over only a few centuries can influence the conditions under which those far slower cycles will operate. The timescales overlap, not equally, but enough that the atmosphere created during the industrial era can outlast the institutions, borders, technologies, and perhaps even languages associated with the period that produced it. Some of the carbon dioxide added to the atmosphere is taken up relatively quickly by plants and the upper ocean. Another portion remains longer. Over centuries, carbon moves deeper into the ocean. Over still longer intervals, reactions involving ocean sediments and weathering on land gradually restore a different balance. There is no single lifetime for atmospheric carbon dioxide. Instead, removal occurs through several processes operating on different clocks. This matters because glacial inception also waits on long clocks. A few thousand years may seem almost incomprehensible from within a human life. For orbital climate, it is a short interval. A pulse of carbon does not need to remain unchanged for 100,000 years to influence the next glaciation. It only needs to keep the planet warm enough during the orbital windows when perennial northern snow might otherwise begin to accumulate. Imagine those windows as opportunities rather than appointments. Orbital geometry gradually moves toward conditions that could favor colder summers. If the atmosphere is cool enough, an ice sheet may begin. If it is not, the opportunity passes. The orbital cycles continue onward. Another favorable combination may not arrive for many thousands of years. This is one reason a relatively modest change in the threshold can create a much larger change in timing. A missed window does not delay glaciations by only a century or two. It can push the possibility into a different part of the orbital sequence. The old climate rhythm then continues without producing the same response. Nothing about the orbit has been broken. The planet has simply become less sensitive to the particular forcing there has once helped ice grow. During the late Pleistocene, large northern ice sheets were common. Climate system repeatedly moved between glacial and interglacial states. That means Earth existed near a range in which orbital changes could be amplified dramatically. A small difference in summer sunlight could be followed by changes in snow cover. Snow cover could alter reflectivity. Ice sheets could change atmospheric circulation. Oceans could reorganize. Carbon dioxide could fall. Dust could increase. Vegetation could shift. Each response influenced the next. The planet behaved like a system capable of moving between two broad modes. Not instantly, not with a perfect threshold, but with enough sensitivity that the astronomical pacing became visible in the geological record. Add greenhouse warming, and the system moves farther from the cold boundary. The same orbital variations still occur. Their ability to initiate large-scale northern glaciation becomes weaker. This does not make orbital cycles irrelevant to climate. Even in a warmer future, they will continue altering seasonal sunlight. They will continue affecting high-latitude summers and winters. Over sufficiently long intervals, they will still form part of Earth's climate background, but a forcing can remain physically real while being overshadowed by a stronger influence. At present, the warming effect of elevated greenhouse gases operates in the opposite direction from the cooling required for glacial inception. That does not mean every place warms equally, nor does it mean winter disappears. Weather continues to vary. Snowstorms continue. Regional cold events continue. Sea ice can fluctuate strongly from year to year. A warming planet can still produce severe winters in particular places. But Continental glaciation is not measured by whether a city experiences a cold season. It is measured by whether snow and ice survive and accumulate across enormous areas over very long periods. That is a completely different scale. The distinction becomes easier to feel when you imagine northern Canada over 10,000 summers. A single unusually cold winter changes very little. Even a century of variable winters may not be enough. The decisive question is whether summer repeatedly fails to remove the accumulated snow. If the answer is yes for long enough, the land begins to whiten permanently. If the answer remains no, the ice sheet never gets started. The future of glaciation is therefore determined less by dramatic cold than by persistent survival. That idea also changes how the word overdue sounds. Nothing is waiting beneath the climate system. No reservoir of cold is building because the Holocene has lasted too long. No planetary mechanism notices that previous interglacials ended after a certain number of millennia and prepares to restore an average. Averages describe histories. They do not command futures. This is especially important because the late Pleistocene climate record is not a set of identical waves. Some glacial cycles were longer, some were shorter, some terminations were larger, some interglacials were warmer in particular regions. Ice sheets differed in geometry. Sea level differed. Carbon dioxide differed. The timing among orbital cycles differed. The 100,000-year pattern itself emerged relatively late in the Quaternary and remains an area of active investigation. Earth's climate has rhythms. It does not have a metronome. There is comfort in understanding that difference because it removes a false sense of approaching inevitability. A new ice age is not standing just beyond the horizon, but the same understanding replaces simplicity with something more interesting. The future remains governed by physical conditions. Those conditions can change. Over tens of thousands of years, the carbon added during the modern era will gradually be redistributed. Over longer spans, chemical weathering will continue removing carbon dioxide. Continents will move, ocean gateways will evolve, mountains will rise and erode. The sun will very gradually become more luminous as it ages on the main sequence. The exact combination that once favored Quaternary glaciation will not remain fixed forever. Eventually, the question becomes larger than the next ice age. How long can Earth remain an icehouse planet at all? To answer that, the view has to widen from orbital cycles measured in tens of thousands of years to geological changes measured in millions. For now, though, the northern ice sheets remain absent. Their old beds are covered by forests, lakes, roads, farmland, and cities. Much of Canada still rises slowly because the crust continues responding to the removal of ice that disappeared thousands of years ago. In Scandinavia, land is also rebounding upward. The vanished glaciers still influence coastlines. Their weight is gone. Their imprint remains. This is one of the more tangible ways to recognize how recent the last glaciation really was. The planet has not fully relaxed from it. Earth's mantle moves slowly. The crust responds over millennia. A place that appears stable on a map may still be rising because an ice sheet no living person has seen once pressed it downward. There are similar memories elsewhere. Great Lakes basins occupy terrain profoundly shaped by ice. Long Island contains glacial sediment left near the former margin of the Laurentide ice sheet. Across northern Europe, moraines and scoured landscapes preserve pathways of vanished glaciers. In the mountains, U-shaped valleys reveal where ice once flowed through terrain now occupied by rivers, roads, or forests. The old glacial world is not hidden. We live inside its abandoned architecture. A present moment landscape can therefore hold two times at once. There is the surface you recognize now, and beneath it, the shape left by a colder climate. For someone resting thousands of kilometers from the nearest ice sheet, that colder Earth may feel remote. Yet the ground, the lakes, and the coastlines of many inhabited regions still carry its geometry. The distance is mostly temporal, not spatial. This gives the future question a different texture. The next ice age is not an approaching repeat of something foreign. It would be the return of a process that helped build much of the landscape already around us. But if it comes, it will not arrive according to a simple schedule inherited from the past. Its possibility depends on whether the climate system once again moves close enough to the glacial threshold. And in the foreseeable geological future, human-caused greenhouse warming has moved that threshold farther away. The orbit continues through its cycles without concern for any of this. Axial tilt decreases and later increases. Precession carries the seasons around the ellipse. Eccentricity grows and shrinks. The astronomical pattern continues whether continents are frozen or green. The ice appears only when Earth is ready to answer. And for the next part of the story, the question becomes what happens when we look beyond that answer into a future where even the long quaternary rhythm may eventually fade into a different kind of planet. Far beyond the next possible glaciation, the problem becomes less about timing and more about whether Earth will continue to possess the conditions that allow large ice ages at all. The quaternary climate system feels permanent because it surrounds us. Antarctica is frozen, Greenland is frozen. Snow returns each winter across high northern latitudes. Mountain glaciers still occupy ranges from Alaska to the Himalaya. But this arrangement is only one chapter in a much longer climate history. Earth has spent great stretches of geological time without permanent ice at either pole. It has also passed through intervals when glaciers spread far beyond anything familiar today. The difference between those worlds did not come from the sun suddenly changing its behavior. It emerged from the slow interaction of continents, oceans, atmospheric carbon dioxide, weathering, biology, and the changing brightness of the sun itself. Those processes have not stopped. Plate tectonics continues beneath every continent. A fingernail may grow faster than some plates move. Yet across millions of years, even a few centimeters annually becomes an ocean basin, a mountain chain, or the closing of a sea. The arrangement of continents matters to ice. A large landmass near a pole can support an enormous ice sheet. A pole covered mostly by ocean behaves differently. The positions of continents also determine where mountain ranges rise, where deserts form, how monsoons circulate, and which rocks are exposed to warm rainfall. They determine where oceans can flow. A narrow seaway can connect two basins. A closing gateway can redirect currents. A widening ocean can establish new pathways for heat. Over geological time, the map of the planet becomes part of the climate machinery. Antarctica offers one of the clearest examples. Its position near the South Pole provides the physical platform for a continental ice sheet. Its isolation by the Southern Ocean helps maintain its cold environment. But Antarctica will not remain in precisely its current setting forever. No continent does. The plate carrying it continues moving. Other plates continue moving around it. Over tens of millions of years, the boundaries of oceans will change. Any attempt to describe a distant future coastline therefore becomes progressively uncertain. The farther forward the calculation reaches, the more tectonic histories can diverge. But the principle remains secure. Future ice will depend partly on future geography. The long carbon cycle will matter just as much. Carbon dioxide enters the atmosphere naturally through volcanic and tectonic processes. It leaves through several pathways, including reactions between carbon dioxide, water, and silicate rocks. Rain absorbs carbon dioxide from the atmosphere and soil. The resulting weak acids react with minerals in exposed rock. Rivers carry dissolved products toward the ocean. Marine chemistry eventually allows part of that carbon to become stored in carbonate sediment. Those sediments can remain locked away for immense spans of time before tectonic processes carry some of their carbon back into the atmosphere. The cycle is slow enough that an entire civilization can rise and vanish without noticing much of it directly. Yet, over millions of years, it acts as a planetary thermostat. When climates are warm and wet, chemical weathering can proceed more rapidly in many regions. That tends to remove carbon dioxide more efficiently. When the planet becomes colder and drier, weathering often slows. Less carbon dioxide is removed. This negative feedback does not hold climate at one exact temperature. Earth's history makes that clear, but it helps prevent the planet from wandering indefinitely in one direction under ordinary geological conditions. Mountains complicate the processes. When tectonic collisions raise fresh rock into warm, rainy environments, weathering can increase. When large volcanic provinces erupt, they can release enormous amounts of carbon dioxide on geological timescales. When continents assemble or break apart, the balance changes again. Carbon therefore travels through a cycle that is inseparable from the moving crust. This is one reason the climate of 100 million years from now cannot be projected simply by extending the orbital cycles we know today. Orbital calculations describe the changing distribution of sunlight. They do not tell us where the continents will be with perfect certainty. They do not specify future volcanic outgassing. They do not specify how mountain building will alter weathering. They do not tell us what biological systems will exist. The farther ahead we look, the more the question shifts from prediction toward physical possibility. Could glaciers return after a long, warm interval? Earth's history says yes. Could a future arrangement make large continental glaciation difficult for tens of millions of years? History says yes to that as well. The planet has already done both. There is another influence that operates on an even longer clock. The sun is slowly changing. A main sequence star like the sun does not maintain exactly the same luminosity throughout its hydrogen-burning life. As hydrogen is converted into helium in the core's composition changes. It contracts and heats. The sun gradually becomes more luminous. The increase is extremely slow from the perspective of human history. Nothing about tomorrow's sunrise will reveal it. Nothing about the next 1,000 years will make it visible to ordinary observation. But across hundreds of millions of years, the effect becomes significant. Earth receives more solar energy. That slow brightening means the background against which future climates develop will not remain the same. The very distant Earth will orbit the same aging star, but under a gradually stronger flow of sunlight. That creates a long-term tendency toward warmer conditions. The carbon cycle can compensate for some of that warming. Higher temperatures can increase weathering under suitable conditions, drawing carbon dioxide down. A lower concentration of greenhouse gases can partly offset a brighter sun. In this sense, rock and atmosphere respond to stellar evolution. The connection is remarkably indirect. Changes deep within the sun influence sunlight reaching Earth. That sunlight influences temperature and rainfall. Temperature and rainfall influence weathering. Weathering changes atmospheric carbon dioxide. And carbon dioxide changes how effectively the atmosphere retains heat. A process beginning in a stellar core becomes linked to rivers running across stone. No single part of the system needs to know that the others exist. Physics provides the connection. Eventually, however, compensation becomes harder. As the sun continues brightening, atmospheric carbon dioxide may decline to levels that increasingly constrain some forms of photosynthesis. Much farther in the future, Earth could become warm enough for the long stability of its oceans to be threatened. Those events lie far beyond the timescale of the next glaciation and carry large uncertainties in their details. They belong to a future measured in hundreds of millions to billions of years. Long before then, the familiar quaternary pattern may already have changed. The Ice Age rhythms that seem so central from our position in time may occupy only a narrow segment of the planet's total history. There is something useful in seeing it this way. The repeated glaciations of the recent past can feel like a permanent pulse. Ice advances, ice retreats, another glaciation begins, another interglacial follows. But the pattern itself had a beginning. Large northern hemisphere ice sheets did not dominate the Cenozoic forever. Their repeated expansion became prominent only within the most recent few million years. If a rhythm can begin, it can also weaken. It can be replaced by another climate state. The Milankovitch cycles would continue. Even then, axial tilt would still vary. Precession would still turn the seasons through orbital geometry. Eccentricity would still alter the shape of Earth's path. But those astronomical changes might no longer produce kilometer-thick ice sheets over Canada or Scandinavia. A warmer atmospheric background could reduce their effect. A different continental arrangement could remove suitable land from high latitudes. Ocean circulations could distribute heat in new ways. The astronomical rhythm could remain, while its geological expression changed almost beyond recognition. This is one of the deeper lessons hidden inside climate records. A cycle in forcings does not guarantee a cycle in outcome. The Earth system translates one into the other, and the translation changes with the state of the planet. You can find a smaller version of that principle in daily life beneath an ordinary sky. The sun rises each morning according to a highly predictable astronomical pattern. Yet the same sunrise can warm a desert, illuminate a snowfield, disappear into fog, or shine onto an ocean whose surface carries heat thousands of kilometers from where it was absorbed. The incoming light may be predictable. The response depends on where it arrives. On geological timescales, Earth behaves in much the same way. Orbital changes provide a repeating celestial pattern. Continents, ice sheets, oceans, and atmosphere determine what that pattern becomes on the surface. The ancient record preserves many versions of the answer. A cryogenian Earth in which ice may have reached tropical latitudes. A carboniferous world with glaciers in the south and wet forests near the equator. An Eocene world warm enough for forests to extend toward the poles. An Oligocene Earth beginning to build major Antarctic ice. A Pleistocene planet repeatedly burying northern continents beneath enormous ice sheets. And the Holocene world, in which cities have spread across landscapes left behind by the last retreat. They are all Earth. No separate planet was required. No change in distance from the Sun, comparable to moving into another orbit, was required. The climate system itself had enough range to create each one. That range can make the modern world feel temporary. In one sense, it is. Every climate state is temporary when viewed across deep time. But temporary does not mean brief. The Greenland ice sheet can persist for many human generations while still being temporary geologically. An interglacial can contain the entirety of recorded history and remain a short interval compared with the age of the planet. A mountain can seem permanent while erosion removes it grain by grain. Deep time does not make the present unreal. It simply changes what permanence means. There may once have been a child standing near the edge of a Pleistocene grassland, watching animals move beneath a sky almost identical to the one above us now. That person could not have known that enormous ice sheets lay beyond the horizon. They could not have calculated precession. They could not have known that the world around them belonged to a glacial interval that would end. The stars would still have risen. The moon would still have crossed the sky. Seasons would have returned. The landscape would have felt like the world itself. In another age, someone standing beside one of the first agricultural settlements could have watched the same familiar celestial motions, while northern ice continued retreating from lands they would never see. The climate background had changed. The sky had not announced it. Today, we occupy another narrow moment. We can measure atmospheric gases. We can drill ancient ice. We can recover sediments from the deep ocean. We can calculate orbital variations that no human being could ever watch directly. For the first time that we know of, one species can recognize the glacial rhythm, while also altering one of the variables that helps determine its future. That does not place humanity outside nature. It does the opposite. It reveals how deeply a technological civilization remains embedded within the same carbon cycle, energy balance, and planetary feedbacks that shaped every earlier climate. The carbon in fossil fuels came from older Earth systems. The oxygen used to burn them was built through biological history. The resulting gases enter an atmosphere governed by molecular physics older than the planet. Our actions are modern. The processes receiving them are ancient, so the distant future cannot be reduced to a simple choice between ice and warmth. There will be orbital cycles. There will be tectonic change. There will be weathering and volcanism. There will be a gradually brighter sun. There will be consequences from carbon already released, followed eventually by conditions we cannot describe in detail. Somewhere within those interacting clocks, opportunities for glaciation may return. Some may pass without ice. Others, under different, if atmospheric and geographic conditions, may allow snow to survive enough summers for an ice sheet to begin again. No one can assign a precise date to that distant threshold. The science is more valuable without pretending that we can. It tells us what the threshold depends upon, and it tells us that the climate future is not controlled by a countdown. The ice returns only when the planet becomes capable of building it. Until then, the old glacial landscapes remain as evidence: polished rock, deep lakes, moraines crossing fields, valleys widened by moving ice, crust still rebounding after the weight has gone. Each one is a physical memory of conditions that once seemed as complete as the present. And above those landscapes, Earth continues along an orbit that never quite repeats, carrying its oceans, continents, atmosphere, and remaining ice into a future shaped by many clocks at once. The farther this journey has moved through time, the less useful the idea of an ice age schedule has become. Earth does not freeze because a fixed number of years has passed. It freezes when many conditions come together. The orbit changes the seasonal distribution of sunlight. The atmosphere determines how much heat is retained. Oceans move energy across the planet. Continents provide places where snow can persist. Ice changes the brightness of the surface. Carbon moves through air, water, life, sediment, and rock. None of these processes works alone, and none follows the same clock. That is why the history of ice is full of repetition without exact repetition. The cryogenian glaciations belonged to a world of different continents, a different atmosphere, and a fainter sun. The late Paleozoic Ice Age unfolded while vast forests altered the carbon cycle, and southern continents carried extensive glaciers. Antarctica froze much later, after tens of millions of years of Cenozoic cooling. Northern Hemisphere ice sheets became dominant only in the recent geological past. The pattern changed each time. Even the familiar Pleistocene rhythm was not constant. Early Quaternary glacial cycles responded strongly to variations in Earth's axial tilt. Later, the system shifted toward longer cycles, in which large ice sheets accumulated over many tens of thousands of years before retreating. The orbit did not suddenly invent a new rule. The planet changed the way it responded. This is the part of the story that matters most when we return to the present. The Holocene is not balanced on the edge of an automatic deadline. Its age alone tells us very little about when another glaciation should begin. The comparison with earlier interglacials is useful only when orbital conditions, atmospheric composition, ice sheet state, and other parts of the climate system are considered with it. Some interglacials ended sooner. Others lasted longer. the present orbital configuration would already make a simple near-term return to glacial conditions unlikely. And the rise in atmospheric greenhouse gases has pushed the system farther from the conditions required for large northern ice sheets to begin accumulating. That conclusion can sound strange when placed beside the long history we have followed. For millions of years, the late Cenozoic climate repeatedly returned to ice. Then one species appeared during the most recent cycles, learned to extract carbon stored in ancient rocks and sediments, and changed the atmospheric background against which the next cycle would unfold. There is no need to make that fact dramatic. Its scale is sufficient. A coal seam may contain carbon fixed by organisms hundreds of millions of years ago. Petroleum may represent the transformed remains of older ecosystems buried beneath sediment. When these materials are brought to the surface and burned, carbon leaves geological storage and returns to the active atmosphere ocean system. The movement happens far faster than the geological processes that created the deposits. That difference in rate is part of what makes the modern change important. Earth has experienced higher carbon dioxide concentrations before. It has experienced warmer climates before. But those facts do not make the present increase irrelevant. Climate responds to physical conditions, not to whether a similar concentration once existed in another geological world. A Cretaceous atmosphere operated above different continents, different ocean gateways, different ecosystems, and different ice sheets. A future climate will inherit the world that exists now. The past provides experiments. It does not provide copies. This is also why the phrase natural cycle can be misleading when used too broadly. Orbital cycles are natural. Volcanic carbon dioxide is natural. Silicate weathering is natural. Ocean circulation is natural. Human beings are part of nature too, but identifying a process as natural does not tell us whether it is responsible for a particular change. Science separates causes by examining their mechanisms, timing, magnitude, and physical signatures. The current warming trend does not match what would be expected from orbital forcing alone. The orbital variations associated with long glacial cycles operate across much longer intervals. Their present configuration does not explain the rapid rise in global temperature observed during the industrial era. That warming is understood primarily through the increase in greenhouse gases produced by human activities. The distinction matters because the future of ice depends on both timescales at once. Orbital geometry will continue changing over tens of thousands of years. The consequences of modern carbon emissions will unfold over centuries, millennia, and beyond. One process does not cancel the existence of the other. They become part of the same future climate system. Eventually, much of the carbon, when released today, will move elsewhere. The ocean will take up more of it. Sediments will absorb some chemical consequences. Weathering will continue. Carbonate minerals will continue forming. Tectonics will continue recycling material between the surface and the interior. On very long timescales, the atmospheric disturbance will diminish, but Earth will not return to the exact climate state that existed before industrialization. There is no rewind mechanism. The orbit will have moved on. Ice sheets will have changed. Sea level will have changed. Ecosystems will have changed. Human societies will have changed in ways no model can project across geological time. The future begins from whatever state the planet reaches next. This has always been true. Every glaciation inherited the world left by the interval before it. Every deglaciation began with ice sheets of particular sizes and shapes. Every interglacial opened beneath a unique orbital configuration. The climate system carries memory. Sometimes that memory is stored in ice, sometimes in ocean temperature, sometimes in forests or deserts, sometimes in the elevation of land still rebounding. after a glacier has disappeared, and sometimes in carbon that remains in the atmosphere long after the event that released it. The next ice age, if it comes in the distant future, will begin from a world carrying all of those histories. It may begin under continents arranged differently from today. It may begin after atmospheric carbon dioxide has fallen far below modern values. It may begin when orbital conditions once again reduce northern summer sunlight enough for snow to survive year after year. Or the broader climate state may shift in ways that make the familiar quaternary pattern less common before another large northern glaciation can develop. At some point, the language itself becomes uncertain. Geological periods are names created by observers looking backward. Future geologists, if any exist, would divide Earth's history. According to evidence we cannot yet see, they would know which ice sheets survived. They would know which coastlines moved. They would know how long the current atmospheric disturbance lasted. They might recognize a renewed glaciation, or they might see the quaternary ice cycles as a climate pattern that weakened before returning. Only much later. We cannot read that record because it has not been written. What we can read is the one beneath us. The sediments on the sea floor, the chemistry trapped inside polar ice, the scratches cut into bedrock beneath former glaciers, the fossil pollen preserved in lake mud, the coral terraces marking former sea levels, the shells of microscopic organisms that once floated in oceans with different temperatures. None of these records tells the future directly. They tell us how the planet responds. That is more useful. They show that ice sheets can expand when summer sunlight weakens under the right atmospheric conditions. They show that greenhouse gases amplify climate changes. They show that oceans can redistribute heat and carbon in ways that reshape entire regions. They show that ice can reinforce its own growth through reflection of sunlight. They show that major climate transitions can unfold unevenly rather than as a smooth line. And they show that the Earth system has more than one stable-looking state. A warm world can remain warm for millions of years. An icehouse can persist through repeated glacial cycles. A nearly frozen planet can eventually thaw. A continent can sit near a pole without a permanent ice sheet and later become buried beneath one. The appearance of permanence is often a consequence of where an observer happens to stand in time. A person living during the Eocene would have known no Antarctic landscape like the one we know. A mammal moving across Pleistocene grassland would have known northern ice sheets as part of the geography of the world. A human born during the Holocene knows coastlines produced by their retreat. Each perspective is local. Deep time connects them. And once they are connected, the original question changes one last time. When will the ice return? The best answer is not a year. It is a set of conditions. The return of continental glaciation requires orbital geometry, favorable enough to reduce high-latitude summer melting. It requires an atmospheric background cool enough for snow to survive. It requires geography capable of supporting large ice sheets. It requires feedbacks that reinforce accumulation instead of removing it. At present, those conditions are not assembled. The orbital cycles continue, but the atmosphere has moved away from glacial inception. Farther ahead, the balance will continue changing. The next opportunity may arrive after the world has become unfamiliar in ways impossible to reconstruct precisely from the present. So there is no hidden countdown beneath the Holocene, no late appointment, no ancient mechanism preparing to correct the calendar. There is only a planet responding to gravity, sunlight, chemistry, rock, ocean, ice, and time. That response has produced frozen continents before. It may do so again. But the ice will not return because history demands repetition. It will return only if the physical world becomes favorable to ice once more. For now, the great northern sheets remain absent. Their former margins lie beneath farms and towns. Their meltwater paths have become rivers. Their basins hold lakes, reflecting modern skies. Their weight is gone from the crust, though the land is still rising where they once pressed downward. Antarctica remains. Greenland remains. Mountain glaciers continue to store smaller memories of cold. And, above them all, Earth moves through its changing orbit, carrying every old climate into a future that is not yet shaped. The ice waits only in possibility.